Thank you very much. I would be remiss in mentioning that I am a co-founder of ClearPath Robotics. There were 4 of us who originally started the company, just to make sure that's clear. So ClearPath, just out of curiosity, who's familiar with ClearPath? Who's heard of us before? Okay, a few people. Great, new crowd. So we're actually located not too far from here. We're in Kitchener-Waterloo. We were founded to support academic research in robotics, in particularly field robotics, but we've done ARMS. We support the PR2 community, for any of you who are familiar with the PR2 robots. So all of that was where we started, and we've since gone beyond that into self-driving vehicles for industrial applications, such as what you see on the board, so on the presentation. So a lot of factory work, a lot of warehouse transport. Basically, unlike Kiva, however, they're operating around people. They're operating in unstructured, very dynamic, unmodified environments, and they move a lot of payload. So that's been something that we started getting into that, I guess, about 3 or 4 years ago. We announced our first product, the Auto 1500, all of which you see here, in September of 2015, and we're continuing to expand. Some of the customers where we have our sites deployed in include General Electric, Caterpillar, John Deere. We just announced Toyota, and about double or triple of that number are also ones we are unable to announce with. So this is really about taking autonomous systems, putting them out in the real world. When we like to contrast ourselves with all the excellent self-driving research which is going out, which is happening on the streets. It is very interesting, very challenging, very fulfilling work. But the big difference between us and them, when you look at it, is that all of this work, all of these robots here are actually in production. They do not have safety drivers. They do not have supervisors. They are there actually doing work. And if there is, in some cases, if there's a minute of downtime or confusion on one of our robots, we hear about it. So that's just to set the stage. And I can also guarantee about zero math in this presentation. So what I'm going to be talking about, I am frantically personally trying to get up to speed, the field that all of you are making headway in. This isn't where I started, but it's obvious to me that this is really something that we can start to bring into our products and take advantage of. So what I'll be talking about is kind of the steps that we're now looking at, now that our product is actually doing this work, the steps that we're taking to bring all of this research work into reality. So I'll just go with a basic example of where reinforcement learning, or we'll just machine learning, artificial intelligence, I'll probably call it by all 3 during the course of this talk. Like a simple system where we have the ad inventory, or we're doing a social media recommendations where we have ad inventory, browsing history, click-throughs coming in, and the output is ad selection. I know, apologies in advance for any of you who are doing this. I'm probably trivializing your work, most definitely. But the key thing that I want to talk about is first, it's a relatively simple input-output program. And the second thing is the worst that can happen. This is my Facebook. I was indeed shopping for desks. On the other hand, I have never stayed in a hostel in my life, nor am I interested in doing so. So this is really the worst that can happen. Now, if we contrast this with, let's say, our AutoM and Auto Vehicle System, we have a number of interconnected pieces of technology, all of which are relatively complicated. We have our localization and mapping, we have generic object detection, we have strategic planning, which is going on board on the robot, we have local and global path planning, we have our control systems, we have various vehicle systems, and that gets into things like batteries, motor degradation. All of that stuff are things that we have to deal with. On top of that, that's all talking to factory systems. It's all talking to task allocation engines. It's talking to fleet maintenance managers and predictive maintenance systems. All of this is happening, and then we have to do this all over again because we've got 10, 20, 30, 40 robots out in the field, all of which is talking together. So you've got a much more complex system here when you start to play with bringing machine learning and artificial intelligence in. And also, the worst that can happen with a system like this is something like that. That's actually, unfortunately, a live video, and someone was killed. So this is the sort of thing. We don't travel quite at highway speeds, but our vehicles do carry 1,500 kilos of weight. They weigh 500 kilos for the heavier ones, and they travel at 10 kilometers an hour inside of factory environments. That is what people tend to call a hazard. So this is the sort of area which has us being very, very careful about how exactly we roll out machine learning and other sorts of unstructured or very unstructured less deterministic, not fully non-deterministic, but less deterministic, and more key, very difficult to introspect and get a breadth of the testing. This is why we're careful. And now a question which often comes up about self-driving technology in general and our vehicles in general is there regulatory guidance? And fundamentally, yes, there is regulatory guidance on a lot of these things. It says do a risk assessment and do what you can to not kill people. Self-driving vehicles are not special in that form. There are many, many industries where you need to do these risk assessments and invent these regulations as you go. For instance, the nuclear power plant industry, that is a very, very dangerous set of control systems to be developing. And there isn't something like the underwriter's lab for nuclear energy. So self-driving vehicles themselves are very similar. However, you have certain things like this. This is IEC 61508, which is the standard for industrial. Basically, if you're building industrial safety software, you're going to be reading this standard. You can imagine not a pleasant afternoon read, or because it takes 2 or 4 weeks of afternoons. And you notice here, this is just a generic table I happen to find here. They talk about software design, development, and architecture design. Anything high safety integrity levels, which is basically at the level of when you may actually end up hurting someone, you need to have a high safety integrity level for your software. They explicitly say artificial intelligence for fault correction, dynamic configuration of the systems is not recommended for SIL 2 through all the way up through SIL 4. So these aren't people who are, and you'll actually notice this is the 2010. This is the 2010 version here. So this is before all this deep learning and reinforcement learning really became into vogue. They're already thinking about where do we use artificial intelligence to look at this, because traditional artificial intelligence, traditional neural networks, large industry was one of the first, and I would say only, adopters of neural networks back before they became cool, so to speak. So this has been anticipated, and people are really, really scared of where you actually bring this into your software systems. This isn't to say don't use it, but it's something to say that maybe you should not rely on a dynamic reconfiguration event to save your life. For example, there are medical standards which are derived from IEC 61508. So SIL 4 is basically if you want to write software for a pacemaker. That's the equivalent. That's the sort of software quality that you would have in SIL 4, where you have a single microcontroller and you probably don't want it to dynamically reconfigure your heart rate. So just wanted to make sure that this is stuff which is being discussed. This is stuff which kind of is things that we need to deal with. Now you can override these regulations yourself, but it is certainly smart to take some of that stuff into account because people have been working through this software for a long time. So when we're looking at view of the disturbing video I just showed and the regulatory guidance, the question is, well, we want to bring, there's so much potential in reinforcement learning, in machine learning, and we still want to be able to take advantage of it. There's still a ton of potential which can be brought into industry. We do believe in the potential for all of this technology, and we believe that building the general robotic worker, if you will, requires all of the advancements that we're doing at institutes like this and that the Vector Institute hopes to accelerate. So here's kind of the 3 steps we've laid out. First, you start by building it the old-fashioned way. Then you target and identify possible enhancements. And then you prototype and benchmark. So the extreme opposite of my approach would be the various individuals and companies who believe that the best way to on-road self-driving vehicles is to grab a bunch of data sets and deep learn everything. That is the complete and polar opposite of my approach. I will be very, very interested to see the results there. But in our experience, it has some problems. So what that means from building things the old-fashioned way, if we're talking about vehicle controls, well, we're not starting with online parameter estimation. We're starting with PID and MPC. We're not starting when we get into path planning through various ways of doing learning by demonstration and proper reinforcement learning on how you get through this environment. You're talking about basic deterministic kinematic lattice planners. Peripheral interfaces, there's all sorts of things we discussed about behavior trees and inferred propositional logic of when the robots lift and lower various peripherals of theirs, turn on and off conveyors, make noises, do all sorts of things like that. But that's still a research point for us. For now, we went into the market using some basic manual configuration. Likewise, there's all sorts of potential with using convnets and the like for 3D object detection, but we're starting with more of a basic sparse keyframes and depth estimation. So there's lasers that we use as well, but just even getting into some of the 3D object detection that we're doing, we start with the basics. Likewise, task allocation, there's all sorts of things you can do when you pump in a lot of information from what a factory wants to do. But it turns out that's pretty hard to debug, and you want to be able to debug that quickly when you have a production supervisor asking you why their parts aren't making it to the line. So we have some very basic user-defined constraints for initial task allocation. And there's all sorts of data analysis you can obviously do when you get your data back and you start bringing back terabytes of production data from your factories. And there's all sorts of, online-based classification, 1980s type stuff, but still generally very useful things. But it turns out you can get a lot done with Microsoft Excel and IPython. So this is all, it's all boring, but on the other hand, it works. So we were able to launch our first vehicle system. From initial launch to first deployment was about a year from announcement, and we did not have a strong research engine behind us. But there is a very, very significant challenge to go from, basically barely announced prototype product to operational in factories. And we did it with a relatively small team, which means efficiency. But it also has another interesting piece of side benefit, is that now you get paid to collect data, which is really interesting for us, is because now all the data sets, we don't have to make up data sets. This is a snapshot I took yesterday, 6,700 live representative real data sets. These are not simulations. Our simulations run nightly. We've built our own little cluster for dynamic robot simulations. But these are all real data sets from real factories. And it's one thing to say, it's very difficult to walk into a factory and say, I want to deploy a robot in your production environment, and I'm going to collect data, and maybe I'll come back and launch a product. Good luck. That's the sort of thing a factory supervisor, they just don't care. A plant manager does not care. But if you go in and say, I'm going to save you all this money, oh, and by the way, can I collect data at the same time? They say, sure, as long as you're collecting me data, you can, as long as you're saving me money, you can basically do whatever you want on some of these data sets. So that's been really interesting for us, is that you can notice the top files here, these include laser scans, they include image data and stuff like that. So that's 19 gigabytes of robot data set, and it just kind of goes down from there. So that's really interesting, obviously, because data set collection is a pain. I mean, I assume every one of you has had to go through the pain of collecting some sort of data sets for machine learning. And the other benefit here is that if I get paid to collect data, I mean, the robots collect the data, and our field teams collect the data. Our internal researchers don't have to collect data. They just kind of wait, and the data just continually flows. This is another one. This is actually production data. This is production data from we'll call it a Fortune 50 company. This is a week of data with 3 autos operating there. So we have things like mission durations, which correlates to factory traffic patterns, which is interesting. So we can start pulling different parameters, types of missions. We can start looking at the various mission distributions, things they're actually asking our systems to do. So at the top is things they're asking our systems to do, how long they're taking to complete, and then at the end gets much more into the histogram of how much data is actually being done. Now this sort of data set collection, as I said, it's really interesting because now we get it for free. I didn't need to ask for any of this data at all. I didn't need to ask someone to do a study. I logged into our system and said, what is this client? I would like a data set. I would like a picture for tomorrow's seminar. What's the data set of last week for a specific use case? So this is interesting as well, because as many of you likely know or are in the process of learning right now, the real trick between large-scale data analysis isn't so much the algorithms, it's how do you get the data of a sufficient quality to do so. And we've automated everything. So now when it gets into things like actually starting to do this prototyping that we're starting on, we have that data sets to start with, which has been really interesting for us. So that's the first step. Once you do it the boring way, the data pipe starts flowing. We're using off-the-shelf parts or off-the-shelf software to collect this data, which has also been really helpful for us. And then the next step there is to identify the enhancements that are available to us. For instance, as I said before, safety must be guaranteed. So what steps can we take which drive up performance and do not decrease safety? What are the steps that can bring our system from a 98% uptime to a 99 or 99.9% uptime because they're able to infer something about the environment? So there's a lot of open potential for us to get into, to start bringing this technology in without having to compromise our safety systems, which has been nice. Likewise, reliability must be assured. So this gets actually into some of the software and user interface designs that humans must be in or on the loop for large changes. So there's certain changes that we can do. We do some machine learning for paths that we've traveled, and those we don't need to bring the humans into the loop for. But when we're talking about automatically optimizing the map, for instance, the rules of the road that we've laid out, you probably want to bring a human into the loop before robots start reversing the direction that they're going down through your factory, because you work to set up a traffic flow, and that's where all the forklifts are driving. And if robots start opposing the flow of traffic, again, angry phone call, probably at 3 in the morning. And the final point, obviously, is prototyping and benchmarking. The right side, this is actually some tests of using it, starting to get into some comms nets out there. You can see the autos are actually being identified as cars, which is really interesting to us. We're not quite sure why. We'll probably do some deconvolution on that and see what's happening. Except in the one particular case where an auto is recognized as a sofa, which has been, it's coming up. But so this is the general, but there it is. But the interesting thing that we've started doing here is these virtually supervised field tests. So what we do there is we deploy a system. We don't let it actually have any impact on the actual robot or the actual robot performance. But the moment where the system would have an impact on the system's performance, it actually collects a log file and sends it back to our server for analysis. So that's the sort of thing where we can actually start saying, we can actually look at it and say, this is what it would have done had we allowed it to be activated, and it collects that data automatically. And then obviously you run it through the release cycle and go back to prototyping. So that really closes off what we believe is a good approach. At least it's not the only approach, but what we believe is a good approach to doing this. Build it the old-fashioned way because there's no substitute for real data. Identify enhancements on a piecemeal basis because deep learning all those things is dangerous. And then prototype and benchmark very extensively because customers do not care about novel algorithms that don't work. So that's everything. Yes?